everyone, I'm Professor Harrison, and welcome back to our module on regression. Today we're going to be covering what ordinary least squares is, and the criterion that sits at the heart of it. We're following Margot, a graduate student piecing together the story her family buried, using regression to make sense of a box of old letters, a stack of published articles, and her family's old financial records. Today she stepped away from the investigation for an hour to catch up on her studies. The task in front of her is fitting a straight line through a cloud of data points and figuring out what it even means for one line to fit a set of points better than another. She turns to the next problem in her coursework. So in the last couple videos, we set up the simple linear regression model. We've got a dependent variable y, an independent variable x, and we want to describe the relationship between them with a straight line. The question we left hanging, however, was this. Out of all the straight lines that we could possibly draw through the data, how do we pick the best one? That's the question that ordinary least squares answers. To make it concrete, say you're trying to predict an apartment's monthly rent from its size in square feet. You collect a handful of apartments and you plot them. You can already see the general trend. Bigger places end up renting for more. So you draw a straight line through the cloud of points, and that line is your prediction. For any apartment, you read off the line at its square footage, and that's the rent that the line says it should go for. Now here's the thing. The line almost never passes exactly through the points. Take a 1,000 square foot apartment. Say your line predicts $1,600 a month, but the apartment actually rents for $1,750. The line missed by about $150, and that miss has a name, and we'll call it the residual. The residual is just the actual value minus the predicted value. So in some sense, it's what really happened minus what the line said was going to happen. So this apartment ends up with a residual of positive $150. It rents for more than what the line predicted. We can take another apartment, a 700 square foot place. The line predicts $1,300 for rent, but it actually rents for $1,200. So the line overpredicted and the residual is negative 100. So every point is going to have a residual. Some positive, some negative, depending on whether the point sits above or below the line. And a good line is one where those residuals are small. The point sits close to the line, and a bad line is one where those points are scattered far away from it. So we want one number that captures how good a line is overall. The natural first idea is that you can just add up the residuals to see how close the line is. But it runs into a problem right away. One common question is why we don't just sum the residuals as they are and call it a day. Well, let's think about what happens. The positive residuals and the negative residuals will end up canceling each other out. For example, our apartment that had 150 for its residual and our apartment that had 100 under for its residual will end up erasing part of each other. You could have a line that misses every single point by a mile, and as long as the misses above and below roughly balance, the residuals would sum to about 0. So you'd end up telling yourself that the line is perfect when in truth it's actually terrible. So adding the raw residuals doesn't work. The fix is to get rid of the signs before we add, and the way that OLS does this is by squaring each residual. This works because regardless of whether the residual is positive or negative, once we square it we end up with a positive. So nothing ends up canceling. So for example, when we square our two apartments, the 150 miss becomes $22,500, and the $100 miss ends up becoming $10,000. Both are going to contribute and push the total up. So squaring does one more thing that turns out to be very useful. It penalizes big misses much more than small ones. A miss of 200 isn't twice as bad as a miss of 100 in the eyes of OLS. It's actually 4 times as bad because we're squaring. So OLS really cares about avoiding large errors. It would rather have a bunch of small misses than one enormous one. So now we add up all these squared residuals across every point in the data. That total is called the sum of squared residuals. You'll see it written as SSR. It's a single number and it measures how badly a given line fits. A small SSR means a tight fit and a large SSR means a loose one. And that gives us the rule at the heart of the whole method. The OLS criterion says, out of all possible lines, we're going to choose the one that makes the sum of squared residuals as small as it can possibly be. So the best fitting line is the one with the smallest total squared error. Now a line is defined by two numbers, the intercept and the slope. So really what we're choosing is those two numbers. We end up looking for the intercept and the slope that together drive the sum of squared residuals down to its minimum. And that should sound familiar. Back in the calculus module, we spent a lot of time on exactly this kind of problem. Taking a function and finding the inputs that make it as small as possible. That's just unconstrained optimization. The sum of squared residuals is just a function of two variables, the intercept and the slope, and we want to minimize it. So we'll see in the next video that OLS really isn't a new kind of math. It's just the regression problem handed over using a tool that we already have. Margot sits back up. Up to now, fitting a line has felt like something you do by eye. You eyeball the cloud of points and you draw something that looks reasonable, hoping that it's close. But in reality, finding the best fit is actually the answer to a very precise question. Which line makes the squared misses the smallest? There's exactly one such line and it can be computed. She makes a note. The thing she's been doing on instinct in her own work has a formula sitting behind it. She just needs to find it. So that's the core idea behind ordinary least squares. For any line, the residual is a gap between what actually happened and what the line predicted. We square those residuals so the positive and negative misses can't cancel, and so large misses count for more. Add them up, and you get the sum of squared residuals, a single number that scores the line. OLS picks the line that makes that number as small as possible, which is just an unconstrained optimization problem in the intercept and the slope.